All right. Welcome, everybody. Welcome to this webinar about programmable integrated photonics. This webinar is being organized by Luceda Photonics as part of our Luceda Academy webinar series. Today we have some very nice speakers, and I would like to introduce you to them. First of all, we are going to hear a talk from Professor Bogart. You already see him here on camera. Wim is a full professor at the Photonics Research Group at Ghent University and IMEC. He specializes in silicon photonics and, of course, programmable photonics. And he's involved in many educational activities, so you will see his presentations are always very interesting. We also have with us Professor Juejun Hu, who is professor at MIT. His research team focuses on novel materials and devices to exploit interactions of light with matter. And we also have with us Dr. Patrick Lowe. He is the CTO of Advanced Microfoundry, which is located in Singapore. He has more than 30 years of experience in semiconductor and optoelectronics industry in USA and Singapore. From the Luceda Photonics side, well, you already heard me talking. Of course, I am marketing and sales application engineer at Luceda, but the design part of the webinar will be given by my colleague Iterio, who you also see here on camera. He's a PDK engineer at Luceda, and he worked together with our colleagues from Luceda China on these examples. So what is today's webinar going to look like? Well, aside from this introduction I'm giving you now, we will hear from Wim first about the why and how of programmable integrated photonics. Professor Juejun Hu is going to talk about advanced materials for programmable photonics, and Patrick Lowe is going to talk about photonics building blocks for this application and user cases. Iterio will finally give you an overview of design and simulation of a programmable PIC. Before we get started, I'd like to do a little marketing. So in April this year, we're going to organize in Brussels Luceda user group meeting. It's going to be very interesting, bringing together users of our software from many different application fields. So stay tuned for registrations that are opening soon. And we also are hiring all the time. Specifically, we are always looking for software and application engineers. So if you're interested, just go on our website and apply, or you can contact us on LinkedIn. We're always happy to have a chat. So this being said, we can get started with the interesting talk. So I'm going to stop sharing my screen, and I give the floor to Wim. So I'm going to spotlight Wim for everybody. I think should be working.
Not yet.
Is it working? Because I'm clicking on it.
Right click on my camera image.
Yeah, spotlight for everyone.
Yeah, so then I should see it appearing myself, but it doesn't show up.
Did it work this morning?
Yeah, this morning worked. Okay.
Okay.
Yes.
Okay.
Okay. Thank you. Let's move out of the way here. Okay. So thank you, Chiara, for the. Maybe I should ask everyone, can you please mute yourself, because I hear several people talking in the background. All right, let's get started. So programmable integrated photonics. There's a couple of words there. Let's dive into what we actually mean with this. When we think about programmable and photonics, which are the key words here in the title, with programmable things, we typically think about manipulating devices in software. A device that has a software interface that controls its behavior. And with photonics, we manipulate light. And usually when we say photonics instead of optics, we talk about light on a very small scale. So just throw these things together, and we want to manipulate light in software on a small scale. Now, what is the motivation to do this? Well, light contains information, and you want to process that. Can you please mute yourselves? Thank you. Okay. Okay, so what type of information is available in light? Well, you have the power of light, you have the intensity profile, phase profile, the wavelength, polarization, you have this kind of angular orbital momentum, etc. But if you want to manipulate such beams of light in a classical way, you typically end up with devices, optical building blocks on an optical table. And that works for small scale experiments. It becomes a bit of a problem if you want to do hundreds or thousands of different manipulations. And the solution is pretty clear. I mean, it's been known already for quite a while. The technology of photonic integrated circuits actually can solve a lot of these issues. By integrating different optical functions on a chip, you can get the same functionality in a much smaller footprint, with typically a much lower cost, especially if you want to make a large number of copies of it, lower power consumption, much more reliable, and eventually also better performance. The same type of benefits as we've seen in electronics. And with electronics, you know, Moore's law, we've seen an exponential increase in the number of building blocks that we can integrate on a chip. And the same kind of scaling law we also know in photonics. So now with silicon photonics, which allows you to really integrate a lot of components on the same chip, we're now getting closer to on the order of 1 million devices per chip. We're not yet there, but you see that that little red dot at the top is already coming pretty close to 10 to the 6th. Now, one particular type of these large scale circuits with lots of components are programmable photonics. And over the past almost 10 years, we've seen now more and more demonstrations of this kind of circuits where light can flow through a number of optical building blocks, which are electrically controlled to manipulate the flow of light, and basically coupling the beams of light together and distributing them over a chip, especially in this kind of mesh where you flow your light from left to right. And this kind of architecture, this unidirectional flow of light in a photonic circuit, is often called a multipath interferometer or a universal linear circuit, and some people also call it a photonic processor. What is the key functionality that we have in such a block or in such a circuit? And that's an optical gate. It's essentially a photonic building block that allows you to tune the coupling of two waves, how much they couple between the two waveguides, and their relative phase delay. So the effective functions that you need to make such a gate is an electro-optic phase shifter and a tunable coupler. And you can actually implement a tunable coupler using electro-optic phase shifters. So this building block is actually the key building block to make such a universal programmable photonic circuit. Now, why do we actually need such programmable circuits? Why would we use this? For what functions? Well, if you consider that that an optical signal is essentially an amplitude and a phase, then the optical signals that go into these circuits can actually represent a set of complex numbers or a vector of complex numbers. And the same can be said for the light waves coming out of that. They all have an intensity and they have a phase, and as a result, they also represent a complex number. The transformation from this input to this output is a linear transformation. And so essentially what's happening is that this function performs a real-time matrix vector multiplication on this vector of optical numbers. And it turns out that matrix vector multiplications are the essential mathematical or numerical operation for a lot of useful applications, especially in pattern recognition, in quantum optics, and artificial neural networks. So it's not a surprise that a lot of the applications and publications on programmable photonics are actually looking into these application spaces. But there's another type of programmable photonic circuits, one that is actually a bit more generic than the circuits that I showed earlier that have light flowing from left to right. These are what we could call recirculating meshes, where instead of the waveguides being organized from left to right, they're now organized in loops, in this case, hexagonal loops, which allows you to both route, switch, and split and filter the light, for instance, by making ring resonators or Mach-Zehnder interferometers in your circuit. And if you then add additional functional blocks like detectors and modulators and amplifiers and fiber ports at the edges of this mesh, you can now make a programmable circuit. You can basically connect these functional building blocks together in any way that you like. And this type of functionality is often called a photonic processor or a photonic FPGA, because it resembles very much an electronic FPGA in the sense that you have functional blocks that are connected together by a programmable interconnection mesh. Now, in both cases, for both types of programmable photonic circuits, we use the same type of optical gate, a device that mixes light and that introduces programmable phase delays. Now, this is quite a bit of a challenge to make these devices actually really good, because you need now circuits that have hundreds or even thousands of these building blocks. So what do we want in such a building block? Well, first of all, we need really good optical gates. That means that they have a compact footprint, a short optical length, low optical loss, low electrical power consumption, because you need many of those on a chip. You don't want the chip to heat up. Low CMOS compatible drive voltage, so on the order of, let's say, between 1 and 5 volts. Preferably fast. You should be able to switch them in megahertz or even gigahertz regime. No crosstalk, and preferably something that can be integrated with all the other functions on a silicon photonic platform. So that's kind of a challenge, because there's no technology today that really ticks all these boxes at the same time. Well, there are some implementations. So you can have implementation based on heaters, on carriers, MEMS, piezo materials, liquid crystals. There's a whole zoo of possible ways to implement a phase shifter, but none of them really gets there yet to this ideal golden specification. Today, most phase shifters in photonic circuits are heaters because they're easy to implement and they actually have a low optical loss, but they're power hungry, their thermal crosstalk is off the scale and actually really complicates the control of your circuits, especially as you scale them up to really large numbers. Alternatives are, for instance, carriers on a silicon photonics platform, but these are really good for fast modulators, but they're way too big and they have too high optical loss to really be used in large-scale cascaded circuits. So what else is there? Well, everything else is a bit more experimental. There's MEMS devices like what we're developing in the projects Morphic and Formic, which do have a very strong effect because you're mechanically moving silicon around. That's a really strong effect on the refractive index. They can be compact and low power, but they're freestanding. So there's some questions on mechanical stability and also how easy this is to integrate in a real large-scale circuit and a standard process. Likewise, there's materials like liquid crystal, which have also a very strong optical birefringence. You can also make very compact phase shifters, but it's a liquid. Do you want liquids on your chip? And it's also a fairly slow effect. So the response time is on the order of milliseconds. And then there's a number of different other techniques like piezo materials, which is a rather weak effect, but it's a low power and low optical loss. There's Pockels effect materials, which could on paper be the ideal phase shifter, but at this point, all the implementations are still too weak to actually be really useful in these large-scale circuits. And then there's phase change materials, which might be a very interesting candidate. And the next presentation actually goes into these materials in much more detail because they have a very strong effect and can be operated at fairly low power because they only need to be switched or actuated when you change their state. But the problem is that most of these materials still are fairly lossy, at least in one of the two states. So but there's room for improvement, and there's a lot of hope that these could actually turn out to be really good. So, but at this point, we're not yet there. So there's no gates that really tick all the boxes. So the scalability of programmable photonic circuits is limited, especially if you also consider that you need hundreds or thousands of these gates on a chip. So each gate needs to have electrical drivers. You need to monitor what's going on the chip. So it becomes a packaging challenge. It becomes a control challenge. Now, if you manage to solve that challenge, and the people in Ipronics, for instance, have already gone a very long way towards establishing such a device, you get something like this, where you have such a tunable waveguide mesh with indeed the detectors and modulators and the fiber interfaces, everything connected together. And then you don't just take that photonic chip, but you also integrate it with the electronic driver chips, with the digital control, with microwave inputs and outputs, and a light source. So you get a full hardware implementation of such a processor. And then next to that, you basically need the software layers to keep everything operating. So you need control loops, you need configuration algorithms, and also a development environment for the users. Now, there's multiple layers of control needed. In such a recirculating mesh, the light can essentially be everywhere. So you need to monitor where all the light is going, and you need to be able to control every individual actuator and make sure it does exactly what it needs to do. On top of that, you need to know how you want to control all your devices. You need to basically select which devices are used for routing, which devices are used to implement the filter, and how the building blocks are connected together. And then on top of that, once you have configured or have figured out how you want to configure your circuit, you need a global control system over your chip that actually makes sure that everything keeps working as intended. And so this whole way of controlling photonic functionality and software completely changes how you design a circuit. Because we all know how we design a circuit today. You draw shapes on a mask, or if you use a PDK, you connect building blocks together with waveguides, which are then translated in shapes on a mask. With a programmable photonic chip, you already have your shapes on a mask. You actually have your chip. You just need to configure every building block that it does exactly as you want. And therefore, the whole development, the whole design process is now a software process where you basically set every individual state. That basically means there's a whole lot of new room for new intellectual property and new innovation on the design side, translating a regular circuit into a programming strategy and a configuration of a programmable PIC and how to control it. Or you could have algorithms that basically take a configuration of a programmable chip and bring that back to a programmable subcircuit onto your own custom chip. And there's a whole lot of other algorithms that could be figured out and it could be used to basically create additional layers of know-how on top of programmable photonics. For instance, you could make a graph representation of your programmable photonic chip, of your waveguide mesh, and then use routing algorithms to do, for instance, multipath routing with collision avoidance inside that graph, or to use distribution networks inside that graph with different objective functions. In the left one, we try to minimize the number of gates that we actually used, while in the right one, we try to minimize the power that was in each waveguide, for instance, to reduce to photon absorption. You also need to keep in mind that this is an analog circuit and all these photonic building blocks are not perfect. So if you program a circuit in your photonic chip, you should be aware that every element in your chip is actually not perfectly functioning as you want it. And as a result, what you will get is, due to these fabrication errors and control errors, is get all kinds of parasitic resonances in your mesh. And you don't need a lot of little errors to really see the effect in your circuit. For instance, in this case, a 1% random variation on the nominal coupling already gives you these spiking ring resonances everywhere in your spectrum. If you go to 3%, the resonances are all over the place. However, there is hope because you can now go with smart software algorithms to try and compensate for that. For instance, instead of changing only the couplers that you need to use to travel to where your light needs to be, you can also optimize the state of all the other couplers to basically quench all these resonances and reduce these parasitic effects. So, and this is just some illustrations of the type of innovations on the software side that you can do with your programmable photonic circuits. So that basically shows that your programmable PICs are more than just photonics. It's photonics, analog electronics, digital electronics, software layers. It's essentially an entire technology stack that needs to come together as a whole to really realize these programmable processes. So does that make these programmable photonic chips the one chip to rule them all? Well, in a way, yes. You can handle many functions. You can combine microwave and optical functions. You have the flexibility to program. But just like in programmable electronics, these larger chips typically have a higher power consumption because all the elements that are there on the chip, you will have higher optical loss. And it might also be more expensive in terms of square millimeters than a custom-made chip. But it saves you a lot in time because you can now use an off-the-shelf chip to prototype your new photonic ideas. And that can really change, that can be a game changer in terms of innovation. So the really breakthrough potential of programmable photonic chips is that it offers a much shorter development time for fast prototyping of new functionality, just like FPGAs in electronics. And therefore, you can address a much larger community because you don't need to design a new chip, you basically program a new chip. Of course, there's quite a few technological challenges to really scale this up, but we're working on that, and there's other groups in the world working on that. And with that, I would like to finish here. I just want to briefly thank all my teammates and collaborators for the results that I've shown here. And otherwise, the only thing I can ask, are there any questions?
If you have any questions and you prefer to write them in the chat, I can also ask them for you. Yeah, go ahead.
Hello. I have my name is Onur Düzgöl. Thank you very much for this very nice presentation. I have a simple question. In this programmable chip, do you only work with the unidirectional flow, or can you have some feedback as well? This is my question, actually.
Yes, yeah, it's a good question. So there's a clear distinction. So well, actually, this picture probably shows it best. In the type of circuits on the right, on the left behind me, the flow is really unidirectional. It goes from left to right. And that also makes the control and quite easy, but it also limits the functionality. With these loops, you can make, you basically have omnidirectional flow of light. You can actually even implement in one of these hexagonal meshes, you can implement a loop mirror that basically makes the circuit a reflector. So you can make feedback loops, you can split your light, make Mach-Zehnder interferometers with delays, you can make ring resonators, you can make combined Mach-Zehnder ring resonator filters, multiple ring filters, etc., by just tuning the couplers and the paths in these rings in this mesh as you want.
Thank you very much.
Other questions?
There is a question from the chat. Hi, Wim. What do you think would be the prospect of packaging in programmable PIC?
It's an interesting question because I think it's one of the main challenges. So especially in the short term, if we take this picture, I mean, this is kind of an idea of what this package could look like. Probably the most elegant way of integrating your many driver electronics with your photonics would be a flip chip approach, or a situation where your drivers are monolithically integrated with your photonics. But the problem with that is that your photonic, you need to be already quite sure and quite certain about the properties of your photonics before you engage into these custom flip chip or monolithically integrated driver circuits. So at this point, the biggest packaging challenge with these programmable photonic chip is basically break out these hundreds of control pads for your heaters or your MEMS devices to classical electronic driver boards that are not as closely integrated onto the photonic chip. But so eventually, the future steps, once technology gets a bit more mature, the packaging problem actually becomes a lot easier rather than more difficult. But okay, it's still quite a challenge. You need the electronics, the photonics, the RF, high-speed interfaces. Everything needs to be thermally controlled. So it's not trivial, definitely not trivial.
Thank you, Wim. There is another question. Do you simulate programmable photonic circuits to arrive at the desired functionality, say a tunable filter? If yes, then what is the technology stack used?
Okay, there's different levels of simulations. So what we don't do is like trying to simulate these devices or these circuits in FDTD. So it's using a circuit simulator. Actually, we use Café from Luceda Photonics. But we have our own layers on top of that to make sure that we don't have to rebuild the circuit every time we make a change. But we have a fairly efficient simulation workflow that can simulate quite large circuits with thousands of components fairly efficiently. How do you configure those circuits? Well, that's a layer that's actually sitting on top of the simulation. You can do that either with iterative approaches. So configure, simulate, and update until you have optimized the configuration of your circuit. Or you can do a number of characterization, or calibration measurements or simulations, and then use that information to control and configure your circuit based on the previously characterized behavior of all your building blocks. But our simulation framework is based on the Café simulator from IPKISS.
All right. So I will ask one more question, then we can keep asking more questions later, because I know that Professor Juejun Hu has a time constraint. Okay. So the next question is, I'm a little bit scared by the power consumption for multiple input signals. Are you investigating other solutions based on thermal tuning? Sorry, other solutions besides thermal tuning?
Well, yes, that's also why I showed a couple of these slides earlier. So the main avenues that I'm personally looking into in the framework of other projects is MEMS devices. So mechanically moving waveguides, which is in terms of power consumption, very, very efficient. It's electrostatic actuation. It almost consumes zero power. It's too low to measure. And liquid crystals, which takes a bit more power consumption because it's an alternate current drive. It's not a direct current drive, but it's also much lower power than a heater. But it's true that using heaters, unless there come techniques to really improve the efficiency of heaters with an order of magnitude or 2 orders of magnitude, heaters will probably not scale up to the really thousands of components that we would need for really scaling up these programmable circuits. So that's a potential bottleneck. And in my opinion, at this point, there's no materials or tuning mechanism yet that really ticks all the requirements that you would need for these really large scale circuits.
Okay, thank you, Wim. So there are a lot of questions coming. Please keep them coming. We have time later for more Q&A. Now I would like to give the word to Professor Juejun Hu from MIT.
Okay.
Hey, thank you very much. Let me try to share my screen here. Okay. Okay, can you see the slides and hear me okay?
Yes, I can see the slides and hear you well.
Okay, great. All right, so today I will also be talking about programmable integrated photonics. And I guess I really don't have to go into any introductions about why this programmable integrated photonics are important, because Wim gave an excellent overview about this technology here. So instead, what I will do is to give you a couple of examples. One is that how we use essentially reconfigurable structures to apply them to realize the actually on-chip spectrometers. And then I'll switch gears and discuss about essentially a different phase shifting mechanism using the non-volatile phase changing materials as a way to alternative to heaters, as Win have actually alluded to. Okay, so first of all, let's take a look at how we actually realize an on-chip spectrometer using this kind of a reconfigurable structures. As you all know, spectrometer is basically a device that takes in a broadband light, and what it gives you is the spectrum, or how the light intensity depends on wavelength. So it's obviously a very important device that has broad applications ranging from sensing to medical imaging. But the challenge nowadays is that any kind of spectrometers, typically you will see these are big benchtop instruments that can be expensive and also bulky. So there's been a strong motivation looking into alternative solutions that are miniaturized. And indeed, what I'm showing here, this is what you can go from Amazon for like 30 bucks. You can carve out the cardboard, package it yourself, make it into a spectrometer. But for this kind of mini spectrometers, almost invariably, their performance is much inferior compared to benchtop counterpart. So now one may ask, is there some kind of fundamental laws that actually limit the performance of these small spectrometers? And indeed, if you look at it, this is actually due to the essentially size scaling law of these devices. Just to take one example, if you think about conventional, essentially dispersive spectrometers, you have light coming in, you send it into some kind of dispersive element. It could be a grating, could be a prism. You then split the light into angularly into for different wavelengths to different locations. But what you can immediately see here is that you need a long optical path length to increase the spatial separation for these different colors or different wavelengths of light. Okay, so then this brings in the trade-off here. This is what we call the linear scaling, where large device give you a better performance. Okay, so when you try to miniaturize it, you take a performance hit. On top of that, this kind of dispersive spectrometer also suffers from a limitation in terms of signal-to-noise ratio, because you're splitting the input light power over many, many channels or many, many detectors. So again, there's a trade-off. If you want high resolution, there's actually essentially signal-to-noise ratio limitation. So I do want to mention that we are definitely not the first group to look into on-chip spectrometers. There's been a lot of excellent prior work, essentially looking into all types of on-chip spectrometer devices. But I just want to mention that for most of these architectures, they also follow this kind of linear scaling law there. So their performance is also constrained by the accessible on-chip footprint. So we have decided to look into a somewhat different architecture a few years back, where we look at this problem here. And what we have come up is an architecture that we call digital Fourier transform, or DFT spectrometer. And the whole idea here is that it comprises of a reconfigurable magenta interferometer. If you look at the two arms here, we have a series of cascaded optical switches that allows us to route light paths from the down waveguide to an up waveguide. We can toggle it back and forth. Okay, and if you toggle the first switch, you get the optical path length difference of DL. If you toggle the second switch, you get 2DL, third switch 4DL, fourth switch 8DL, and so on and so forth. Now, what's really unique about this architecture is that any permutation of the switch state would then be able to give you an arbitrary integral multiple of DL path length difference between these two arms here. So for example, if you want to say 9DL path length difference, you just toggle a first switch, they give you 1DL, you then toggle your fourth switch, which give you 8DL, and then combine, you get 9DL. So the total number of optical states that the system can furnish is essentially given by 2 to the j's power, where j is the number of optical switches in the system. And you can also prove that all the important parameters, such as spectral resolution or spectral channel count, they all scale with 2 to the j's power. So this unique exponential scaling essentially means that every time you want to actually double the performance of the device, you just add one single device, right? You immediately can double the resolution, double the spectral channel count. So this is also a secret why we can actually build such a spectrometer, so it's a very compact footprint, and yet offering a very high performance. So then this table just compares this technology with some of the other on-chip spectrometer designs. In addition to the exponential scaling that it empowers this very high performance, I also want to mention that, as I mentioned, this device also does not require essentially splitting the input signal over multiple detectors. So there's also a signal-to-noise ratio advantage there. And in addition, because we only need to use a single detector, this becomes advantageous, especially if you're trying to use it for infrared applications, where a linear array of detectors can get very expensive. So with this idea, a few years back, we then actually went ahead and actually demonstrated this prototype device here, where we use a 6 thermal optic switch to actually create a spectrometer. So in this case, 2 to the 6th power is 64. This device can afford a total of 64 spectral data points. And we then actually package it with a fiber optic input output, temperature control, electronics to do signal processing. So what you end up getting here is just a plug and play spectrometer module. If you want to use it, just plug in the fiber into the light source, click a few buttons on the computer, and then it's going to spit out the full spectrum for you. Now, what I also want to mention here is that the 6-switch module obviously is not the limit here. The one advantage is that we can easily scale the performance by simply adding number of switches. So this is one more module we demonstrated, in this case in silicon nitride platform. We have a total of 14 switches that then affords a total of over 4,000 spectral channels. That gives us less than 0.1 nanometer resolution across the bandwidth from about 1260 nanometer to 1650 nanometer. And this makes this chip scale spectrometer having performance that's already comparable compared to a benchtop optical spectrum analyzers. So just to summarize here, what I have discussed to you is a technology that enables essentially a small, robust, and also high-performance spectrometer that can be easily produced using standard silicon photonic technologies. Okay. So next, I'm going to switch gears a little bit and then talk about a different way to realize this kind of optical phase shifters or reprogrammable photonics using the phase changing materials. And the motivation here, of course, is very well discussed by Professor Bogart in his previous talk, that if you use these thermal-optic phase shifters, they are very power hungry. There's a lot of thermal crosstalk. So we are looking into alternative options. They are essentially non-volatile, requiring only energy consumption where you actually toggle the switch. And then outside that, they will actually maintain the optical state without having to require energy input. So the solution we're looking into here is to use a class of materials called phase changing materials. And they can switch between two structure states, either amorphous or crystalline. And what's unique about this material is that when you switch between these two states, there's a huge contrast in terms of the electrical and optical properties. So these are actually not new materials. If you look at previous work, people have already extensively used them for like rewritable CDs and DVDs, as well as electronic memories using the structure state to record digital ones and zeros. But if you just simply copy the material people use in this electronic industry, the challenge there is that these materials typically exhibit large optical loss. If you look at this optical constant chart here, there's a huge index contrast, but there's also a large optical absorption coming in here, okay? And there's limited applications if you have large optical parasitic loss for these materials. So that's why a few years back, we have actually looked into developing a new bi-stage transparent phase changing material. So the example here is actually GSST, germanium, antimony, selenium, tellurium. What's remarkable about this material is that it exhibits a large index contrast of 1.4, but at the same time, both crystalline and amorphous state are almost completely transparent across the entire infrared wavelength range. So I also want to mention that we are certainly not the only group that look into this kind of bi-stage transparent optical phase changing materials. So later on, they have a group also reporting alternative materials such as antimony sulfide or antimony selenide. And if you look at this one example here, this optical constant of antimony selenide, at the telecom wavelength range, it is actually again transparent at both structure states, and also a distant index contrast about 0.8. So then with these materials, we can actually integrate them into photonic integrated circuits. And then one question that comes up is how we actually switch them reversibly between the two structure states. So going into amorphous to crystalline state, what we do is we input energy pulse that's rapidly low in amplitude, but has a long duration. This will bring up the material to above the crystallization temperature, so all the atoms can then move around and find a thermodynamically stable state, which is crystalline state. On the other hand, if you go to crystalline to the amorphous state, then what you do is you launch a large amplitude but very short pulse. So you'll melt the material into liquid state, and you quickly quench down to essentially maintain this kind of liquid-like amorphous state. So these energy pulses can be applied using lasers, okay, an ultra-fast laser, or alternatively using integrated microheater to actuate the phase transition. So in my group, we have been mostly focusing on electrothermal switching here because it's amenable to integration into a standard CMOS fabrication process flow. So speaking of that, we have been in collaboration over the past few years with MIT Lincoln Laboratory. What they have been able to do is to actually seamlessly integrate these materials into their standard silicon photonic foundry fabrication flow. So what I'm showing you here, this is actually the sputtering system they use in their directly located in their facilities there. They have spent more than 2 years to essentially look into how to encapsulate these materials, how to process them to avoid any potential contamination into other on-chip silicon photonic devices. So in the end, what we're able to do is to essentially process everything in the same process here using their standard PDK components without having to actually do any kind of backend integration, okay? So this is actually the process flow that was used by our collaborators. Basically, you started out with a dope silicon. This dope silicon essentially can act as both a light guiding media, but also as its resistive heaters to trigger the phase transition. And then after that, you can embed it into devices, process this phase changing materials, encapsulate it to prevent any contamination to other on-chip devices. Now next, let's take a look at how these devices perform. So in this schematic here, this is the basic architecture of our non-volatile phase shifter. We have essentially a rich waveguide with dope silicon here. So it's both a light guiding media, and you can also pass current through it to control the phase transition. We can then directly deposit this phase changing material on top, so that we can actually, when we change the structure state here, that we can tune the effective index of waveguide and therefore induce a phase delay. One critical design parameter here is actually the doping concentration of the heaters here. Because if you go to a very high doping concentration, you actually increase free carrier loss. But if you go to a low doping concentration, the serial resistance actually increases, and therefore you need higher voltage to actually switch these devices. So we pick a doping concentration of the order of about 10 to the 18. This is sort of the optimal point that gives you a decent switching voltage, but also a reasonably low free carrier absorption loss. Now, with this kind of non-volatile phase shifter, we can integrate it into all type of photonic devices. So one example here, this is actually a 2x2 magenta interferometer. So by changing the phase of these materials, you can then toggle light between the two different optical waveguide paths. So from this device, we have actually measured a phase shift of 0.0 pi per micron length. So that means to get a pi phase delay, all we need is a device that's 11 microns in length. So it's a lot more compact compared to many other kind of phase shifters. And at the same time, the insertion loss is also only as low as 0.15 dB. And a lot of that actually comes from the fact that we have non-optimized doping design, as well as also the phase changing material integration in terms of basically because we have a rectangular patch sitting on top of the waveguide. So there's quite some scattering loss if light comes in here at this junction region here. So with optimized design, we can actually push this insertion loss even low to below 0.1 dB here, because we are using a bi-state transparent phase changing materials. And similarly, we can also integrate this kind of phase shifters onto a micro-ring resonator, and we can realize very consistent multi-state tuning. What we've also proven is that this material is very stable once you tune it to a specific structural state. So once you have switched it, and you can stay there for more than a couple of months, and basically you still maintain exactly the same resonant wavelengths. So you can also use this kind of material as a way to do post-fabrication trimming of fabricated photonic devices. Okay, now you may wonder why we actually care about this kind of device. What can they be used for? So some examples here. This is actually some work done by Walter Solcher's group at George Washington University. And what they've done is actually they've used our phase changing materials to actually create, in this case, a 4-bit or 16-level electrically programmable optical memory here. What they've also demonstrated is that they can actually switch this memory device for more than 500,000 cycles without seeing any performance degradation. So with this kind of building blocks, the next step they have actually demonstrated is actually a partial differential equation solver using essentially analog computing nodes made of this phase changing materials. So again, due to the time limit, I won't go into too much details here, but you are certainly more than welcome to look into the details within this archive papers, the links I'm showing here. So one last application I just want to mention here is that we can also use this kind of phase changing materials as a way to facilitate wafer level photonic testing. So the challenge we are trying to solve here is that we want to be able to develop a way to enable wafer scale photonic testing prior to essentially singulation of the photonic wafers into individual dies. And the typical way of doing that is to create essentially this kind of tap couplers, which are basically directional couplers that will split a small fraction of power from the main photonic circuit. And then they will direct this power into a testing port, so you can then characterize the performance of the circuit there. The downside, however, is that this kind of tap couplers is actually permanent structures, right? So it means that any power you split out from the main photonic circuit would constitute a permanent optical loss because you cannot remove them after even the testing is done. So the idea we have is fairly simple. If you use phase changing materials, okay, and you can essentially create a tap coupler that's optically transient. So initially, when the material is deposited, the phase changing material is in the amorphous state, and then the waveguide of the testing port will be phase matched to the main photonic integrated circuit. So that you can couple a small fraction of light going to the testing port and then perform all the testing functions. And then once you are done, you just do a simple wafer scale furnace annealing. And then by doing that, you then transform all these couplers into a crystalline state. And this changes the effective index, so it disrupts the phase matching condition between two waveguides. And therefore, you end up getting essentially no light coupling into the waveguide. So essentially, this tap core becomes invisible optically to the main photonic circuits. And by doing so, you can suppress any parasitic loss coming from this testing port. So this is actually a result we have actually experimentally obtained. We show that we can actually use it to actually characterize the photonic circuits very well. And in the on state, we can couple about 6% of optical power, which is necessary for optical testing. But when we transform it into off state, the insertion loss becomes as low as 0.01 dB, almost completely negligible here. We have also shown that this technology is applicable both to silicon and also silicon nitride photonic platforms. So this could really be used for a lot of advanced photonic characterization applications on the wafer scale. So now just to conclude here, I of course want to acknowledge many of our collaborators. Without them, we would not be able to complete all this different work here. Lincoln Labs, our colleagues at Lincoln Lab, UCF, Walker Soldiers Group at George Washington University, as well as Aka Majanda's group at the University of Washington. And I also want to, of course, thank the hardworking grad students and postdocs in my group that actually did all the work here. Specifically, I want to call out Derek Kita, who is a former student who actually developed the DFT spectrometers, as well as my former postdoc Carlos Rios, as well as my former student Yifei Zhang, were the ones actually behind this phase changing materials photonics work. So with that, I'm going to conclude my talk. We have to take questions. Thank you very much.
Thank you very much for your talk. How much time do you have until you have to leave?
I have a few minutes. Yeah.
Okay. So you can ask questions by unmuting yourself if you want, or otherwise I will read them from the chat. Okay, so we already have a question. I wonder what are the major limits of PCM?
Sure. Okay. So I think for PCMs, the main limitations here, one is actually still the switching voltage. If you look at the voltage you need to switch this material, because in this here have fairly high temperatures, you would typically still require of the order of 10 volts to switch in, and that could be high for many applications there. The other problem that sometimes people encounter is how to actually realize very reliable multi-level switching. Okay, not just like on-off states, but you want to do essentially analog type of switching between these devices. So one solution we come up with, this is in collaboration with Walter Soldiers Group, is that we, instead of using just one piece, one chip of phase changing materials, and you try to control the structure state between to create a mixture of amorphous and crystalline states, what we can do is that we actually split up the long phase shifter into many segments. One of them, let's say, is L. The second one is 2L. The next one is 4L. Next one 8L. So then, essentially, by switching each of them between the two endpoint states, be amorphous and fully crystalline, we will be able to then actually generate any kind of intermediate phase shifts in between them. So this way is actually more reliable than trying to control to get a mixture of two phases in this case. But this is something we are still trying to work on, right? We are trying to essentially try to extend beyond just 16 levels. Can we actually do it like 32 or 64 levels, right? As some other people have demonstrated. So these are the things I think that people still need to work on. And then last but not least, of course, is that we need to be able to actually expand the integration of these materials into standard CMOS fabrication process flow. And again, that could still be a challenge, even though we have demonstrated some initial progress, for example, integration with a Lincoln Lab process there.
Thank you so much. We have another question. Is the PCM compatible for fabrication in CMOS compatible foundries?
Great question. That's actually what I just mentioned here. So I would say in general, no, at this point. Like I said, we have demonstrated integration of this material directly with the silicon photonic process in Lincoln Labs. What they were able to do is actually they have to apply essentially encapsulation coating, for example, around these materials, and they have tested, spent enormous amount of time to essentially clear this material, ensure that once they are properly encapsulated, they don't contaminate and cause performance degradation of any other surrounding on-chip devices. We basically need to essentially scale this process also to other more industrial, larger scale foundries as well. I believe there's definitely a path moving forward, especially if you think about these phase shifting materials. They are already being used in like phase shifting memories, right? And by Intel and other companies. So there's definitely a path getting forward. I guess the question here is that we need to find a sufficiently large market for this kind of programmable non-volatile photonics. If we have that, I think that's definitely a motivation to move them into standard foundries.
That's a good answer. All right. So I think there are no more questions for the moment, but I motivate everybody to keep writing questions in the chat. If you have them, we can always ask them later. Thank you again, Juejun, for your presentation. I would like now to give the virtual mic to Dr. Patrick Lowe from AMF.
Thank you.
You can see my slides and hear me?
Yes, I can see your slides and hear you well.
Great. I'm going to turn off my camera here. Sorry, I'm going to turn off my camera here. Okay, let me go ahead. Is it okay?
Yes, you can see it full screen.
Yeah, thank you. I think this webinar features a very interesting topic. Basically, it's very dear to my heart, the programmable integrated photonics, because it covers two key elements. One is the program, the other one the integrated photonics. This I thank Luceda Photonics for this invitations. AMF has been partnering with the Luceda Photonics for a long time, with Luceda supporting AMF PDKs for several generations already. Now, as both AMF Photonics, AMF and the Luceda Photonics plays a very important part in the whole ecosystem for the silicon photonics industry, and has been a long time active promoters for the technology towards the industrialization and also commercialization. So it's only natural for us to have the great interest and also with the other parties to discuss about the relevant technology. The previous two speakers give a very good background introductions already and talk about the technology, so on and so forth. So I'm going to skip quite a bit in my presentation. I'm just go give a little bit introduction of AMF and also talk about the case studies, the cases that using our platform to realize the programmable applications. Yeah. So here's the brief outline. So I introduce AMF very quickly. Then we'll discuss about AMF PDK on the device building blocks and also relevant specifics with the programmable. Subsequently, I hope I can devote more times to discuss some recent cases of applications and which are implemented in our platform and also previously with IME before the spin-off. So for many of you are familiar with AMF or AMF, as you know, AMF is a leading commercial pure silicon photonics foundries. As a trusted manufacturing partners, though AMF is in Singapore, but we have been servicing clients globally, Europe, Asia, and also with large portfolios in Japan, North America, and China as well. So we work towards to deliver reliable and predictable foundry outcome, focus on the safety, quality, delivery, and customer according to the customer needs. So our goal is to become the industrial or de facto foundry centers. So not only do we provide a complete 8-inch manufacturing lines with 90 nanometer nodes for the silicon photonics and also relevant MEMS productions. But over the years, we also have developed a sizable portfolio of 90 differentiate IPs covering the devices, process, and integration. So this enables us to provide a unique PDK and custom designs and manufacturing and supports on top of what the different material system require, covering different optical bands and across the different market sectors. So that's include silicon nitride on oxides, silicon nitride on SOI, very recently start to include silicon nitride on glass. So specific on the service portfolio, technically on manufacturing line itself, we have expertise support from our dedicated teams with veteran CMOS foundry experienced staff, so which includes the quality control team as well. So on reliability, on the photonic wafer fabrication, AMF offers a complete service from prototyping and volume productions. Fabrication for production with volume maturity, we have been doing this for day in, day out for the last 5 years already. So on design aspect, it has pre-developed IP and with continuous upgrades of the PDKs. So therefore, the customer can build their products according to the application requirement, leveraging on those established PDK and test and verify on the silicon already. So on the testing areas, AMF has a wafer level optical electrical testing, and also start to look into the probing for the non-good die, because people are looking at whole wafer yield now. So it's very interesting to know the KGDs and also give a yield response. So along with the MEMS capability for making a relevant wafer level I/O, so this is what it's important for the standard equipped optical I/O. So therefore, as a wafer and chip manufacturing, AMF is quite considered as a one-stop shops from a customer usage point of views. So let me skip on this. So I'll say the customer base coming from various market sectors and with wider interesting application areas. So what's relevant to this particular webinar's topic is on the computing, so which is the programmable part of it. So here's the bit of marketing. So if any of you are interested, here's the email, so you can send it to us to understand more that what we are offering. So back to the technology specifics. So what is offered in our PDKs? So the PDK can be categorized by material and device operations for specific application. Therefore, it determines the specific optical bands required. So the PDK was designed around those bands. So since the beginning, AMF has started providing PDK devices to our customers to facilitate their design and speed up the tape out and also the experimental cycles. So PDK has been evolved to what we call as PDK 3.5 with more 70 devices available that containing 6 libraries implemented in AMF 5 major integration platform. So the current PDK is sufficient enough versatile, covering most of the relevant material that include SOIs, different flavor of the silicon nitrides, as I mentioned, focusing for different bands. So main focus are the C bands and O bands. Customer can freely do the combination through different type of mutations of those devices libraries and implement on the silicon photonics platforms. So from the left to right, so device types include low loss I/O ports, low loss guiding and routing waveguides, the mode and polarization and manipulators, phase shifters, and high bands active. That's include a modulating device and also fault detectors. So basically, besides, we also demonstrate devices in visible light regions for biosensing, and also that's include the LiDAR application as well. So in addition to standard PDK devices, we are also quite flexible for customization requests to develop the needed devices and the standard cells, and are constantly expanding as well. That's why we have a different versions being released over the years. So in the new years, in 2023, we planning to have a new PDK released as well. So for instance, on the LiDAR specific, and also the other one is for silicon nitride PDK as well for emergent applications. So now for today's discussions, what are the relevant specifics to programmable and also the next level as the reconfigurables? So I borrowed this graph from one of the designs that published, and also based on the work has been done in AMF platform. So for programmable photonics chips, that typically, as Wing already explained very well in the previous talk, it needs additional attention is the following. So you have a mesh topology. So basically you have a forward only a mesh and also circulating mesh along with various type of a configuration. That's the be it triangular, binary, rectangle, square, hexagonal, so on and so forth. So within the typical and also the key building elements are the 2x2 analog tunable optical gates with 2 input NZIs, directional couplers. So the coupler has like say 3 dB splits or partial splits for different type of ratios, which is tunable. Then followed by the two outputs NZIs. So the gate delivers the functions of a pass throughs, cross, and also a partial redirect. For each of the pathways, phase shifters along the way. This is why the programmable functionality can be realized. So also you have the actuators and also tunable coupler and phase shifters. So on the monitor side, you need to have power to monitoring the by measuring monitoring the amplitudes and also by the phase. For RF and the microwave needs, so you have it needs high bandwidth modulators, typically at the input end, and also the photo detector at the output end. Then as the standard structures, as I mentioned, we need the structures to serve the optical IOs because all the optical signal needs to get in and out, and also the electrical signals go along with it. One is the control and also the output. Of course, as the device gets longer, with multiple gates and also tuning knobs added, it needs a light source and it needs a light source anyways, and also regularly you might need the amplifier locally for some of the circuitries. So specifically for key features of phase shifters in programmable photonics, it needs a low insertion loss, modulation loss, and also low being power efficient and also free from the crosstalk. So now what are these building elements do and what are they enabling? So I give a few cases examples that has been done over the years. I think this is the very classical examples that back to 2016 and 2017. So this is the two works that published in Nature Photonics back to back in the issues. So this is what I'm saying. In fact, the concept of programmable in photonics is not entirely new in today's context. In retrospect, it seems quite interesting. The reason I put these two works side together, if you look at the chip-wise, they're almost coming from the same chip, but address a different different application. One is on the classical sense, and the other one is for the quantum application. So this is why it illustrates quite well about the versatile of which is being programmable or repurposed application out of the same similar chips back to the time of 2016 and 2017. So I roughly read out from the applications on original purpose and how these come about. So in the first case, for instance, the backgrounds for classical sense, the artificial neural networks are computational network models inspired by signal processing in the brains. For instance, simulating and improving devices performance for many of such as the learning task, including speech and object recognition. However, the existing electronic-based computing hardware is inefficient at implementing this neural networks, in large part because much of it was designed by the von Neumann computing architectures, and significant efforts has been made, although to develop the electronic architecture, but implementation are obvious because it's using the electron as the medians. So as we can see from the top graph, which displays the new architecture based on optical, for fully optical neural networks, they're using the unique advantage of the optics for the signal processing. So basically, what's promised is the speed enhancement can be done 100 times over the state-of-the-art devices, and also 100 times in power efficiencies for the conventional learning task. So this work experimentally demonstrates essential concepts, which was implemented using the very simple programmable silicon photonics-based chip processor. And along the way, on the second cases, it provides a very good platforms to simulate the various cases in terms of how the quantum transport states, that what the sensitivity is, because the environmental noise and disorders plays a critical roles in the quantum particles and the wave transport in the complex media that include solid states and biological systems. So therefore, in their demonstrations, it uses the map of a row of the disorder in quantum transports using, so again, leveraging on the silicon photonics based programmable chips consisting of a mesh of ADA generalized beam splitters, programmable on the microsecond scales. So in their demonstration, over 60,000 transport experiments, large sample size, they observe several distinct transport regions that include environmental assisted quantum transports, and also quantum, they call it quantum Goldilocks region in strong and static disordered discrete time systems. So this is why you see it's very interesting. Out of the same chips, you'll be able to accomplish all of this. So this work, although it's back to 2016, but for the last month, the economists decide this work in a very good context, along with the other works for artificial intelligence and also the rise of optical computing. I like the title of the articles in the actual magazines. It's called as Enlightened Computing. It gives the enlightenment about the new age, how the computing is about, and also from my perspective to see how the integrated photonics, especially in the silicon photonics, how those enlightenment can come about. And this is the second case, the very recent work in 2021. And similarly, other similar works as shown here as the case study as development for optical neural chips for implementing complex valued neural networks. So in this work, integrated photonics chips for implementing complex valued neural networks in which the light signal are encoded and manipulated by both the magnitude and also the phase during the initial input preparation and also network evolutions. So operating mechanism is based on the input preparation, weight manipulation, weight modifications, and a coherent detection. And all those are integrated onto a single chip. So this is the chips I described earlier in my PDK discussion. Basically, it maps out all the devices that are being required. So the performance of this complex value neural chips was tested in 4 scenarios: simple Boolean task, species classifications of various data sets, classifying nonlinear data sets, core and spiral, and also handwriting recognition. This is a very classical AI type of testing experiments. So from the experimental and test, strong learning capability with high accuracy, fast convergence, and also the capability to construct nonlinear decision boundaries achieved by this chips compared to its real value counterparts. So the last slides So it shows quite interesting application as well, which touch upon on the free space. So this is the work illustrates with the capability also with the programmable. Both are from multiple the collaboration from various groups from Lino, Grassi, Max Planck, and also Stanford University groups along with others in the free space concept. And both published very recently as well. So again, let me read out the background and a rough sketch of the work as following. So free space optics is an attractive technology to meet the ever-growing demands for wireless bandwidth in next generation networks. To increase the spectral efficiency of the free space links, transmission over spectral division multiplexing can be exploited, where orthogonal light beams have to be shaped according to suitable amplitude, phase, and polarization profiles. So as you can see, the requirement of this, so it does needs quite big programmable and tunings in order for all the devices to work together. So the work at the left shows the programmable photonics chip that consisting of a photonics mesh of tunable MZIs can be used as adaptive multi-beam receivers for a free space communication link. So the circuit can be self-configured to simultaneously receive and separated with a negligible mutual crosstalk. The signal carried by orthogonal beams sharing the same wavelengths and polarizations. So this feature is demonstrated on signal pairs is arriving at the receiver from orthogonal directional diversity, and also being shaped according to the different orthogonal or spatial modes. So it covers the mode diversity, even in the presence of some mixing during the propagations. So the performance of this programmable mesh as the adaptive multi-beam receiver is assessed by means of a data channel transmission at 10 gigabits at the wavelengths of in the C-band region. But the optical bandwidth of the receiver over 40 nanometer allows the use at a much higher data rates as well in the WDM and also the SDM multiplexing links. So along the similar lines as the right side works shows, in this work, a reconfigurable photonics chip is used to optically sample and processing free space beams so as to implement a spatial resolving detectors of amplitude and phase. So in my summary here, so from the this recent development, we can see more application being exploited, and also I see some of the this has been reached to in the photonics regions, has reached to some production and commercial stage, which give a lot of confidence for more exploration, for more applications. I think for the programmable, it will take some time to reach into the same stage to enjoy the attentions as the the silicon photonics technology being deployed in the data center for transceivers. But we're going to see more and more because the confidence and also adoption rates over the years. So the silicon photonics, as you will see for the last 5 to 6 years or so, is no longer a lab technology. It really is the technology that we've seen have a higher commercial value. So with those, we will see more and more investments from the communities and also more efforts into it. I think the history seems to be repeating what the electronics were, as we see from the, as Wayne was discussed about the electronic FPGAs. So we're going to see more and more towards the photonics FPGA for more or less for the same type of purpose, but also address for different type of concerns. And I think the audience will share the same enthusiasm as I have to embrace that kind of opportunities for the research purpose as well as for the commercial purpose. So as part of the supply chain, just like Luceda and also long-time promoters, as I mentioned, to the industries, we have a more responsibility than anyone else to build even a stronger ecosystem to grow the industry together by averaging the technology. So as closing remarks, please use the Foundry and the EDAs such as Luceda as your true partners for your dreams. So thank you very much.
Thank you very much, Patrick. I really liked your closing remark. It is very true. So everybody in the photonics ecosystem has a role to play. We have ours, and we are always happy to hear from all of you who actually do the research and bring products to the market, how we can help you better. So we are always open to such a conversation. So the floor is open to some questions. If there are any at this point, as before, you can either unmute yourself or type in the chat if you want. We will have a Q&A session at the end of the webinar after Iterio's presentation. So if you have any questions and you want to ask later, we can address your questions at the end. So I will now give the floor to Iterio then, also because we are running a little bit late. So Iterio, as I mentioned in the beginning, he's PDK engineer at Luceda. First of all, I would like to thank Patrick again and give the floor to Iterio. So Iterio is going to present about how to actually design these circuits. So he's going to show how you can use our IPKISS Photonics Design Platform to create the layout and simulate a programmable PIC.
Thank you very much, Chiara. Can everybody hear me and see my screen?
Yes.
Perfect. So hello, everyone, and thanks again for this opportunity. So in this presentation, I'm going to talk about how to design and simulate a programmable photonic circuit with our software IPKISS. So in particular, I'm going to talk about a little bit of an introduction about who we are at Luceda and what our software IPKISS does, and also how it can benefit the design of programmable photonic circuits. Then we're going to focus on the layout of such a programmable photonic circuit. We're going to see how we're going to actually make that layout in our software. And then we're going to discuss using simulations how we can change the functionality of that same circuit by simply changing a couple of voltages. And we're going to do that by showing, as I mentioned, simulations. But first things first, who are we and what do we do? Well, we are Luceda Photonics. We're a relatively young company, this year about 9 years old. We are founded in Belgium, so our headquarters is in a city called Dendermonde, but we also have a subsidiary in Shanghai. Now, the name comes from, on one hand, lux, which means light in Latin. And then on the other hand comes EDA, which everybody's familiar with. It's electronic design automation. So we know that EDA is already very popular in the electronics world, but what we want to do is we're trying to bring that same functionality to photonic IC designers. And to do so, we have created the IPKISS Photonics Design Platform. So this software basically taps into all the stages of, well, basically a photonic design project. So it starts with, for example, the component design, where you can make, for example, the layout, and you can make the layout parametric. We also provide some links to third-party software such as Lumerical in order to perform some physical simulations on that component. But then once your component is designed, we can then stitch those components together into, well, a full circuit. So again, this, just like the component can be parametric, the circuit can also be parametric. But important to note here is that, as was already mentioned in previous presentations, we also have a built-in circuit simulator. So on that, once we have our circuit layout ready, we can perform circuit simulations on that, and in order to assess the performance. And since the circuit layout is parametric, so is the simulation, so are the simulations as well. And then, of course, it doesn't stop there. We can then also do some validation of our designs. We have some tools for that. We have then we can also do some other things, such as maybe some measurement processing. And the nice thing about this is that all those things can be done on a single platform and using a single scripting language, which is Python. Now, in addition to our software IPKISS, we also provide PDKs. Now, this is important because, of course, you need to rely on foundries to fabricate your circuits. And so these PDKs, they basically contain those foundry-specific settings, not only the layers, but also, for example, the design rules, the standard building blocks and their models. And then, of course, once you have that, you can, again, perform circuit simulations on your circuits. And you can basically assess the expected performance of your design. And then just like the IPKISS software, it's also made in Python. And we also provide, again, some tools to do some automated testing, some quality assurance. We can also export our layout to, for example, like open access formats. And as you can see here, we provide a lot of PDKs for many different material platforms, indium phosphide, silicon nitride, silicon, you name it, from all around the world. So that gives you a lot of flexibility. So, but why is this important now for programmable photonics? Well, like I mentioned before, there is a very tight link between the layout and the simulations. So, for example, if you change the layout, then the models are automatically updated as well. So that means that if you create these parametric cells, if you just change, for example, one layout parameter, and we will see an example later on, then also the models will automatically be updated. And as you can see here also, another thing to mention here is that these programmable photonic ICs, well, they become very complex very quickly. So it's also important to provide some semi-automated routing, because otherwise you're going to spend more time actually doing the routing and, drawing all the optical waveguides and metal wires. You'll spend more time on that than actually, doing the design of the key building blocks. And then, of course, again, these PDKs, you can use them to make sure that your programmable photonic IC is, well, manufacturable. And then you can, of course, also do some quality assurance and testing. So now that we know what the strengths are of IPKISS, let's now focus on the design of an actual programmable photonic circuit layout. So this is what we want. You have a bunch of unit cells, and then they're all routed. So how do we start designing this? Well, first of all, we have to focus on the main building block. And as Wim mentioned in his talk, the main building block in this case is like a switch. In this case, it will be a Mach-Zehnder interferometer. So how does a Mach-Zehnder interferometer look like? Well, it consists of a bunch of building blocks. So it consists of two directional couplers that split the light 50-50. Then it contains a heated waveguide where you can do the phase shifting. And then it contains a regular waveguide. Now, in this example, we're assuming that all these components are integrated in a silicon nitride layer of, a generic silicon SiFab PDK, which is provided with our software. So how do we code it? Well, for example, the first thing what you need to do is instantiate those components. So here you can see that you instantiate the directional coupler, then the heater, and then the waveguides. An important thing that I need to mention here is that these components are parametric. And there are two ways you can change the parameter. So on one hand, you can change the parameter, the layout parameter directly. So for example, here you can see that you have a parameter heater length. And you change as a user, you can change the value. And then of course, the length of the heater can be automatically changed or adapted. Or you can also use performance metrics like with the power fraction. Remember, there is a tight link between the layout and the simulations. So in this way, that means you can link the layout with certain performance metrics in a very straightforward way. So in this case, if you want a certain power fraction of, let's say, 0.5, it will correspond to a certain, directional coupler length. And if you, for example, increase the power fraction to 0.7, then the length will automatically be increased. So that gives you a lot of flexibility to design your circuits. Then, of course, once you have all your components ready, you need to all stitch them together in your, MZI switch. So this is done in this code. So you can place your component like here, the directional coupler. Here you can then place your heater and your non-heated waveguide. And as you can see, just like the components are parametric, you can also make the circuit itself parametric. For example, you can add like a length difference between the top and the bottom arm. But in this example, we're just going to assume that, in this example, the length difference is 0. Here you can see how you place the second directional coupler. And then, as I mentioned before, you have this semi-automated routing. Well, here you can see an example of that. So what you can see here is that all the ports of the directional coupler, the heated waveguide and the non-heated waveguide are connected to each other. And the only thing that you need to tell the software is the port names. That's it. There are some other parameters that you can add to fine-tune it, but this gives it this is a very straightforward way of basically connecting your components together and creating a circuit. Now, as I mentioned before, once your layout is ready, you can perform calculation or you can perform circuit simulation. So in this case, we're going to look at S-matrix calculations that we can do with our built-in software Café. And as we mentioned before, so in generally, this MZI has 3 different configurations. So here you can see, for example, the bar configuration, which means that light from the bottom input will be redirected to the bottom output, and then vice versa, from the top input will be directed to the top output. With the coupler configuration, light from, the bottom input will be redirected to both of the outputs, and then the same thing for the top input. And then the cross, that will be reversed. So light from the bottom input will be redirected to the top output, and then vice versa for the top input. And these voltages that you can see here, they are actually automatically calculated. Well, they are calculated with the S-matrix calculations, and basically we provide some optimization scripts so that these voltages are automatically calculated. And since everything is done in Python, this can be done very conveniently. So now that we know what we have as a unit cell, and now that we know how it works, we can stitch them all together into an actual programmable photonic circuit. So here you can see the code. It's very simple. So we made this also parametric. One of the parameters is the unit cell that you want to, that make up the photonic integrated circuit, which is in this case the MZI that I just shown you. The other parameters are how many unit cells do you want in the horizontal direction or the vertical direction. In this case, it will be 3 in both directions. And then finally, you can also specify like a length of the unit cell. So for example, if you want to make it a bit bigger, you can add some straight sections to it. This might give you maybe a bit space for the routing of the metal tracks. Now, of course, this is the wave. So this is the photonic integrated circuit without any routing. Of course, you still need to connect those optical input-output ports to, in this case, edge couplers left and right? Because otherwise, how will you couple the light in from your fibers? But it's not just for the optical waveguides. Of course, you also need to think about the electrical wires, right? So you can see that the MZI here has pads on the heater. So how we implemented it is that the electrical ports on the horizontal MZIs, or the signal pads, they are routed to the top of your chip, while the electrical ports of the vertical MZIs, they are routed to the bottom. Then finally, you also have a ground ports on all the MZI switches, and they are routed basically to a common ground. And you can see that as more ground ports are connected to each other, you can also see that the width of the metal pad increases in order to avoid improve the resistance. And then, like I mentioned before, the parametricity is very important. So if you, for example, change the number of unit cells along any dimension, then also your design gets automatically updated. And I would like to show you actually an example of that. So here you can see an example of, let's say, the 3x3 mesh, or at least the 3x3 photonic integrated circuit that we already introduced. But let's say I want to have, 4 columns. So I'm just going to change that, and now I'm going to see where I can, that I can rerun the script. So I just changed 1 digit. And so you can see, if you look at the code, that here, for example, I import our PDK, with all the technology settings and the building blocks. And voila, here already your non-routed circuit is ready. And then there are some other libraries. Well, I have, for example, import the other classes. And then, for example, here I instantiate the unit cell, which is the MZI switch. Then here I plug it in into the class that creates the square, or at least the non-routed programmable photonic circuit. And then this instance is then given to this class where you can now see the result of it. So this is then the routed circuit. And again, this is, I just use one single digit, and very conveniently, I have like well, a perfect circuit that I can immediately send to the foundry to well, to be fabricated. But let's continue now with the presentation. So now that we've discussed the layout and things are basically ready on that side, now let's have a look at the simulations, like a few of examples that we can actually achieve. So as I mentioned before, like it contains a lot of switches, and each of the switches have a certain voltage. So how are we actually going to program this? Well, as you can see here on this slide, these switches, they are kind of placed into a matrix, right? So like in this case, a horizontal matrix. So then likewise, it makes sense to also put those voltage values into matrices as well. And this is what you can see here. So this is 4 by 3. And here you also have a matrix 4 by 3 that basically, you know, contains all the voltages on each of the MZIs. And the same thing applies then also to the vertically placed MZI switches. And here you can see then also the matrix for that. Now, to give an example to make it a little bit more clear, let's look at the tunable delay line. So we have the input, the zeroed input port and the zeroed output port, and we want to tune basically the time delay that exists between those two ports. So what we do is we make sure that the actual length, optical length, changes by, you know, changing the switches, as you can see here. And here you can see, for example, how we do that. So in this case, the 3 bottom MZIs are horizontal MZIs are configured to bar, and here you can see that the voltage corresponding to the bar configuration are well implemented. All the other switches are not really relevant, except here, of course, because here you route the light to the, well, you know, to the second arm or to the second row, and here you can see that you then also change it to bar. And then the same thing here. These switches are now used in. Let me just take this. Let's change it here. 1 second. Voila. So you can see now that this is cross and this is cross. So these 2 bottom MZIs, and then here now you've changed it from bar to cross, and then the same thing here. You need to make sure that this is also bar. So you can see the voltages. And then of course this is for the horizontal MZIs. You also need to do the same thing for the vertical MZIs. So you can see that you need to well configure them as cross in the cross configuration, and the same thing here. But then for the next row, you basically need to configure them as bar, right? So that's how you again configure in the program your programmable photonic circuits. So how do the simulations look like? Well, we use optical pulses at the input ports, and then we look at the response at the output ports, out 0, and we calculate that response with get time response, because you know it's a dynamic time domain simulation. And here you can see that now that as basically the delay length increases, you will also see that the delay itself increases. So you can see that this pulse arrives much later than these 2 pulses, for example, and then the same thing between these 2 pulses. So this shows that the circuit works as intended. So that's for tunable delay. Let's have a look at tunable routing. So what I mean with tunable routing is that you have a bunch of input ports here, and then you have a bunch of output ports, and you want to route the signal from the input ports to, you know, the particular output port. So for example, in this case, you want to route the light at the zeroed input ports to the first output ports. And here you can see how the light would flow within your circuit, and how then also the well, the switches need to be configured. Then in this case, for example, if you want to route light from the 7th input port to the 5th output port, you have to configure your switches like this. And then, of course, yeah, for the same, this is a different routing network. And then, yeah, you can see that then, of course, just like with the tunable delay, where we had to, you know, give the voltage matrices, this is no different here. I won't go into detail here, but I think you get the message of this. So let's have a look at the simulations. So in this case, we use rectangular optical pulses that are a bit delayed in order to ease the visualization at the input ports. And then we look at the output ports. So let's look at one example here. So let's look at the in zero signal. So here you can see that the rectangular pulse at in zero is actually routed to the pulse, or at least the output the first output as expected from the switching matrix, or as expected from the schematic. The same thing for the in 7 to out 5. You can see here the light at the 7th input is actually routed to the 5th output, as you can see from the colors. And then with this other routing matrix, it's kind of the same story. For example, let's just take an example. In 3 is routed to out 6, and you can see that in appearing in your simulations. In 3 is here, and then the dashed line out 6 corresponds then with input 3. And then the final example that we can have a look at is a tunable ring resonator. So in this case, a tunable ring resonator is basically we're gonna create a ring resonator, and then we're gonna change the amount of unit cells that it consists of. So again, you have to give voltage matrices in a certain way with certain voltages, and here you can see. I'm not going to go into detail, but here you can see how those are configured. And when you do the simulations, in this case, we're not going to rely on time domain simulations, because S matrix simulations are way more efficient, and we also provide that option in the simulator. And here you can see, for example, that if you have a single unit cell, that the free spectral range, or the spectral distance between the dips, is much larger than if you have 2 unit cells. And this makes sense because 2 unit cells basically have a longer ring length, and we know that the free spectral range is inversely proportional with the ring length. So this is exactly what we would expect. There's one thing though, you can see that the dips do not go all the way to 0, but you can also change that, because you have this V coupler voltage here, which basically corresponds to this switch here. And what you can do is you can basically change the V coupler value in order to make sure that you achieve critical coupling, or where the light goes to 0 or close to 0. And then this way you will, because mostly the rings are operating in this regime, but then you can just tune this V coupler bias. And again, there are many more examples, and I can say much more about this, but of course time is a little bit limited. So if you want to know more details, please have a look at our tutorial on Luceda Academy, of which you can see here the link. And yeah, that concludes my presentation. If you have any questions, feel free to ask. Thank you.
Thank you so much. Sorry. Thank you so much, Iterio. We already had one question, which was which simulation tool is being used in these results?
Well, so this simulation tool is basically part of IPKISS. So in IPKISS, we have a built-in cafe simulator, circuit simulator, and the circuit simulator is called Cafe. And as shown in the presentation, what is nice about this is that if you, for example, have, let me show here, if you, for example, have this circuit, for example, this programmable photonic circuit, this layout has automatically a circuit model associated with that. So if you instantiate, your layout or your design, you can immediately perform circuit simulations on that with our built-in Cafe simulator. And the nice thing about Cafe simulator is that it's bidirectional. It is dynamic, so you can, include active components, passive components, you name it. So that gives you a lot of flexibility.
Thank you, Iterio. Is the tool able to automatically set the proper path for each input?
Sorry, come again?
Is the tool, so I guess IPKISS and the Cafe simulator, is a tool able to automatically set the proper path for each input?
Okay. So like, for example, if you
I guess if you select each to know where the light path should go for each input that you have in your circuit.
Well, in theory, that is possible. Well, in this example, we kind of did it manually. But as also Wim mentioned, like all these switches, they are not perfect. So you probably need to do some additional things in order to, you also have to apply some biases to all these other voltages in order to make sure that what your circuit does actually, is doing in practice. But of course, yeah, that's a whole other field. So yes, in theory, this is possible, but it's a little bit more complex than, yeah, in this case, we just gave like a manual example, like, okay, we just set manually the switches. But then in practice, it will be a little bit more cumbersome and maybe will require some, some machine learning as well.
Another question is, how does the CAFE simulator compare to FDTD?
Well, FTTD are mainly physical simulations. So like that's really on the, the component design level. For example, you want to simulate the coupling between like two waveguides in order to create a directional coupler, and you use and you want to simulate like what is the coupling in the bend sections, or are the reflections. Of course, then that's, let's say, a relatively slow simulation. But of course, from the FTTD simulation, you can create circuit level properties, such as what is the coupling as a function of waveguide width, or what is the coupling as a function of the wavelength, and things like this. Those are the parameters that you can retrieve from FTTD simulations, and these parameters are then used within CAFE to do your circuit level simulation. So again, FTTD is on the component level, but then from the component level, you can retrieve then your circuit level parameters that are then used with the CAFE circuit simulator to then simulate your whole circuit. So it's a bit comparing apples and oranges, because those two simulators kind of work in conjunction with each other. Yeah.
And maybe just to add one thing, for example, if you take the directional couplers that we are using in this circuit, those have been simulated with FDTD, and then the results of the simulation are used in this circuit. Maybe I'm going back a little bit, and I will ask again some questions to Wim that we still had from before. I think normally Wim should still be here. I think.
Yes, I am, but
okay.
Not for long. I have to...
So just a couple of questions, just to make sure. I promise I would ask later. So is it possible to build programmable PICs which integrates also nonlinear phenomena, such as stimulated Brillouin scattering? What things should be considered on the design process?
Well, it's definitely possible. I mean, every optical function that you can integrate on a chip, you could in principle incorporate in a programmable PIC. The question then is, how are you going to use that functionality, for what purpose, and how well can you control it? So there's no reason why you shouldn't be able, if you have a technique to integrate Brillouin scattering in a PIC, then you can also integrate it in a programmable PIC. But then figuring out how to program or how to manipulate that's another challenge. The reason that programmable photonic circuits are still in a conceptually fairly simple stage, like these square meshes that we still see on the screen, or the simple forward-only circuits, the multipath interferometers, is that it's already challenging enough at the moment to get it to work. I can imagine that once the basic platform becomes something that is really useful and operational, that you'll see people trying to integrate all kinds of additional novel building blocks on those programmable photonic chips to do all kinds of stuff that we haven't thought about today.
Great, thank you. One question to conclude the webinar. I think it's a nice closing question. Could you comment on the chances of success that there will be an efficient, usable photonic FPGA in the future, in whichever technology, whether it's thermal MEMS, etc.?
Yeah, so the chance of success, I think, is very close to 100%, because we didn't specify what future is. So probably in the 24th century, they'll have photonic chips. No, I think the horizon is much shorter, unless there's this like really unforeseen catastrophes. It's fairly certain that programmable photonics will become a reality. And I mean, just to give an example, I already mentioned that in my presentation, Ipronics already has a functional small-scale programmable, general-purpose programmable photonic chip. Also for quantum applications, neuromorphic applications, there's several companies that have operational programmable photonic chips. Maybe not fully general purpose, and maybe not as powerful as they need to be to really become super useful and super generic for all kinds of purposes, like electronic FPGAs, but already these chips exist. So I think it's not a matter of if, it's a matter of when. Was there a second part of your question? Maybe I forgot to answer that.
No, that was it. It was one question. Yeah. Thank you so much. I would like to close here now the webinar, as we are already a little bit late compared to the plan. So I would like to thank all the speakers for your contribution, which of course made this webinar possible. And thank all the participants for being here with us and asking all these questions. I apologize for all the questions we could not address. I do appreciate the motivation to ask and the interest. So thank you all again, and I will send the link to the recording to everybody, so you can rewatch this anytime you want. Thank you.
Thank
Bye-bye.
you for organizing this. Bye-bye.
Bye-bye.